عليكم. This is lecture number 2, Physics 281, Vibrations and Waves. In this lecture, I will discuss the effect of the transient term on the forced oscillator equation, and then discuss the example of isolating a platform given in the textbook. The mechanical equation of motion for the forced oscillator, we already know that it is given by mx double dot plus rx dot plus sx or kx equal f0 cosine omega t. The inhomogeneous term, which is f0 cosine omega t, represents the driving force and leads to what we call it steady-state solution. The homogeneous solution of this equation is called the transient solution. Therefore, we have two solutions. We have to add them together. So the net or the displacement is given by x homogeneous plus x particular. The first term, again, it represents the transient solution, and the second term represents the steady-state solution. The first term varies with time as exponential minus r times t over 2m, and this dies away. The figure here shows how this x, total x, varies with time. As you can see, the system settled down to the steady-state solution. Now the second point is to solve the problem of isolating a platform from a vibrating floor. The platform has mass m and connected in parallel by two springs. Each spring has a stiffness k over 2, and there is also a damping force connecting to the platform m. The equilibrium position for these springs is given for the springs and the platform is given by y, or represented by y. The floor at the bottom of the figure oscillates as a cosine omega t. Now the question is to find y as function of omega and a, and then look for the maximum of this displacement y. The effective displacement of the spring is y minus x. Now the equation of motion is given by m y double dot minus 2k over 2 is equal to minus 2k over 2y minus x. I multiplied by 2 because we have two springs connected with the mass m in parallel, and we know in this case, as we discussed in chapter 1, we have to add them together. Like the capacitors, if they are connected in series, we have to take the reciprocal of the stiffness. Now the last term of this equation is the damping term, which is given by minus r times y dot minus x dot. Now this is the equation of motion. We know that x is given by a some amplitude cosine omega t. It has certain frequency. In order to solve this equation for y, let's use a transformation x capital equal y minus x small. Then the first derivative is y dot small minus x dot small. Another derivative, x double dot capital equal y double dot small minus x double dot small. but we know that x equal a cosine omega t. So x double dot is a minus a omega square cosine omega t. Substitute in this expression, we get that y double dot equal x capital double dot minus a omega square cosine plus minus a omega square cosine omega t. Then take this value and substitute it in the equation of motion up. We get mx capital double dot minus ma omega square cosine omega t plus rx capital dot plus kx capital equals 0. Rearrange to get mx double dot plus rx dot plus kx equal ma omega square cosine omega t. We met this equation before. It looks like the forced oscillator at the beginning of this chapter. We write this equation here in the red box, and I call it equation number 1. X capital double dot plus bx dot, b is r over m, plus omega 0 squared, x capital, omega 0 squared is k over m. In the book it's s over m, and it's equal to the ma omega square over m cosine omega t. Now to solve this differential equation, it's a second order differential equation which has inhomogeneous part. We already know, if you look at equation 2 in this slide, we already solved this equation, which is x double dot plus bx dot small plus omega square. There's a missing x here. You have to add x equal f0 over m cosine omega t. The particular solution is xp equal f0 over omega z sub m sine omega t minus phi. You know all what is the meaning of all these symbols. Now if we compare equation 1 with 2, we can get the solution of equation 1. So the solution is ma omega square over omega z sub m sine omega t minus phi, or ma omega cancel one of the omegas, numerator and denominator, over zm sine omega t minus phi. So x capital P now is y minus x, but we are looking for y small. Y small is equal x capital P plus x small. So now we have two waves. One is ma omega over zm sine omega t minus phi, plus the second one is a cosine omega t. We have to put them in this form: y equals some amplitude sine omega t minus gamma. Now we have to find what's eta and what's gamma. Okay, we will use complex analysis for that. The first thing is to write cosine omega t as a sine. So cosine omega t is sine omega t minus pi over 2. Now the two waves together can be written as a small sine omega t minus phi plus b small sine omega t minus pi over 2, where a small, this should be a small not a capital, equal a omega m over zm, and b small is a capital. We have to write this expression as eta sine omega t minus gamma. Take the imaginary part of a e to the power I omega t minus phi plus b e to the power I omega t minus pi over 2 and simplify it. This is equal a, the imaginary part, is equal A sine omega t minus phi plus B sine omega t minus pi over 2 now. Let's take the term between the two brackets. Take exponential I omega t as a common factor. Then we have A exponential minus I phi. Exponential minus I phi is equal A cosine phi minus IA sine phi plus the second term e to minus pi over 2, which is minus I b sine pi over 2. And this is given by e to the power I omega t times a cosine phi plus I into minus I sine phi minus b. This is the term between two brackets has a real and imaginary part. We have to put this in a polar form. First, we have to find what's z square m, which is a square cosine square phi plus a square sine square phi plus b square minus 2ab sine phi, which is equal sine square use sine square phi plus cosine square phi equal 1. Then we left with a square plus b square minus 2ab sine phi. Now we have a square omega square. Substitute for a small. I said this is a small, not a capital. A square omega square m square over z square m plus b square, which is a square, minus 2a small, which is 2a capital omega m over zm times a sine phi. We know sine phi is m omega minus k over omega over zm. This is known from previous lectures. Now we have to simplify this expression. As you can see, there is some cancellation. And then finally you get eta square is a square over z square m into r square plus k square over omega square. So y is, you have to take the square root of eta, is a over z sub m square root of r square plus k square over omega t sine omega t minus gamma. This is gamma, not phi. This is a new phase angle. When you add this two waves together, this figure shows gamma. Gamma, the tan of this angle equal a sine phi plus b over a cosine phi. We are interested actually in y over a, which is function of omega, and then we have to look at the maximum, as it at the beginning. We have to look at the maximum of y maximum over a. Now we know y is given by this red expression where eta is m square root r square plus k square over omega square. Now substitute for y maximum, and notice that z sub m is square root of r square plus omega m minus k over omega, the whole thing square. And then we have to simplify this expression, as you see here, and then we get finally this lovely expression. Y over a is square root omega 0 to the power 4 plus omega square times b square. B square, recall that b square is r over m, the whole thing over omega square to the power 4 plus omega square b square plus omega square into omega square minus 2 omega 0 square. Now the maximum of this by inspection, because it takes a lot of steps to find this maximum, so by inspection this occurs, the maximum of this expression y max over a occurs at omega square equal twice of omega 0 square. Omega 0 square is the frequency, the square of the frequency of the free oscillation. Now we have the three cases. Omega square is greater than 2 omega square 0, or lesser or equal to 1. the first one leads to attenuation case. The second one leads to amplified. We already discussed this before. So the important is here is to make omega 0 for the system as low as possible. Thank you.